The scores for this test were a little lower than the other ones. I think the class average was like 73%, in between an 8 and a 9. If you want to talk about the test, come to office hours, and I'd be happy to talk about how it was scored or whatever. Anybody have any questions about either of the problems? I mean, there are examples from the homework that we've done pretty similarly to both of these, but anybody have any questions about, like, was anyone confused about anything that you'd like an answer to? Yep.
I just didn't understand how to do the first one.
Okay. Okay, yeah, the first one was, I didn't look problem by problem, but for the most part it seemed like people, were understood what to do on the second one, but the first one was kind of going back a ways, and a lot of people didn't remember how to do that one. So exam 3, number 1. So we had a pulley with 2 masses. You might ask why the 10 kilogram is smaller than the 5 kilogram. Yeah, right. This one's full of rabbits, that's why. This one's hollow. And then this is connected to a spaceship that's accelerating upwards at 1 meter per second squared. And we want to calculate the acceleration vector of the 10 kilogram mass. Well, let's first draw the free body diagrams, and then we'll think about the accelerations. That's where things are a little, get a little tricky. So a free body diagram of the 10 is just the tension and the weight. And free body diagram of the 5 is just the tension and the weight. And it's the same tension because it's the same cable. Yeah, that's right. And so now we have to think about the acceleration. So we're used to doing this problem with a coordinate system fixed in the pulley. Okay, that's how the easy version of this problem where the thing isn't accelerating, we put our coordinate system fixed in the pulley. So what I'm going to do is that same thing, but then I'm going to use relative motion to calculate the true acceleration of the things. So the acceleration of, the acceleration of the 10 relative to the ground is equal to the acceleration of the 10 relative to the origin plus the acceleration of the origin relative to the ground. And the acceleration of the origin relative to the ground, since I'm using a coordinate system moving with the pulley, this is the one that's 0, 1. That's given. The acceleration of the 10 relative to the origin, I'll call that 0. I'll call that 0 A10 for now. And then for the 5 kilogram, the acceleration of the 5 relative to the ground is equal to the acceleration of the 5 relative to the origin plus the acceleration of the origin relative to the ground. This one again is 0, 1. The acceleration of the 5 relative to the origin is, I'll call this just 0, A5. So the only assumptions we've made so far, that shouldn't be a vector. The only assumption we've made so far is that there's only a y component, only a vertical component to the acceleration. But now there's a relationship between, if you're in this coordinate system fixed to the pulley, there's a relationship between the acceleration of the 10 and the acceleration of the 5. If the 5 rises an inch, the 10 has to drop an inch. And so you can think of it as like A5 is equal to, we'll just call that A, and that's equal to negative A10. And so if you put this all together, you get, so, well, A10 relative to the origin is equal to 0, negative A. A5, oh, I said ground, but I said origin, but wrote ground. So this is the acceleration of 10 relative to the origin. Acceleration of 5 relative to the origin is 0A. And now put it back with the relative motion equation, and you get that the acceleration of the 10 relative to the ground, that's the thing we want for Newton's second law, is equal to 0, negative A plus 1. And the acceleration of the 5 relative to the ground is 0, positive A plus 1. And now we can put those together into Newton's second law. So Newton's second law for the 10 says 0, 10 plus 0, negative 98.1 is equal to 10 times the acceleration of the 10 relative to the ground, 0, negative A plus 1. Newton's second law for the 5 says 0t plus 0, negative 49.05 is equal to 5 times 0, positive A plus 1. And so now you have a system of two equations, two variables. I'll write this as t minus 98.1 is equal to negative 10a plus 10. And I'll write the second one, you know, the negative of this one is negative t plus 49.05 is equal to negative 5a minus 5. And then add those two together, and you get negative 49.05 is equal to negative 15a plus 5. So a is equal to 54.05 divided by 15, which I think is 3.6, something like this, if I remember right. And then you're not quite done, because that's just the variable. Now you have to plug that into this to get the acceleration of 10. So the acceleration of the 10 is equal to 0, and then negative 3.603 plus 1, so negative 2.603. So if you compare it to the simple version of this problem where that pulley isn't accelerating, you do this exactly the same way. The only difference is when you write in the accelerations, you have to deal with that relative motion. Any other questions about that one? Okay. So the last time we had class was Monday, and we were working on this. So we're going back to kinematics and kinetics of particles and rotating coordinate systems. And we had a problem like this, where we had a disk. That's a terrible disk. That will not stand. Okay. So we have this disk connected to a rotating, whatchamacallit, this whole system is rotating with a constant 5 radians per second. This angle is 45 degrees. The length here is 1 meter, and the disk is rotating also with a constant angular velocity of 10 radians per second. And at this instant, this point P, we want to find the acceleration of that. Also the disk radius is 0.6 meters. And what we had established so far was, we had decided on a coordinate system. So our coordinate system was going to be here. X, Y, Z. And so is that coordinate system rotating? Well, it's fixed on that. So this coordinate system we decided had to be, there's no way to do this problem if that coordinate system isn't rotating with the horse. So yes, this coordinate system is rotating. So that coordinate system rotates at 5 radians per second about the negative y-axis. Does the origin accelerate? Nope. So we don't have to use relative motion. So all we have to use is this equation. The acceleration of p is equal to the acceleration of p that's observed in that green coordinate system plus omega, capital Omega dot crossed with the position vector plus 2 times capital Omega crossed with the observed velocity vector of p plus capital Omega cross quantity Omega cross p. And we had established that the position vector is 1.131, 0.283, And with the coordinate system, we chose capital omega is equal to 0, negative 5, 0. And capital omega dot, since it's a constant angular velocity, is 0. So the next thing we had to do in order to apply this rotational coordinate system equation is come up with the acceleration of p and the velocity of p that would be observed in this coordinate system. So then what we want to do for that is forget about all this happening and just, what if we had a problem where this was fixed to the ground and you had a disk rotating around? How would you do that calculation? Okay, so we need the velocity of p observed and the acceleration of p observed in the coordinate system. Okay, that's a circular motion problem. It has one difference from most of the circular motion problems we deal with. The axis of rotation is at a funny angle. Okay, so we have to come up with an expression for that axis, come up with a unit vector in the direction of that axis of rotation, and then multiply that by the angular, velocity, angular speed, I guess. So the right-hand rule says that the axis of that rotation is this way. Okay, going straight out at 45 degrees between the positive x and positive y. Any questions about that? So now we just have to come up with a unit vector in that direction. Okay, so that's circular motion. Circular motion. Following the right-hand rule about this axis, where that's x, that's y, and this is 45 degrees. So we need this unit vector. So what's the unit vector in that direction? Yeah, right, exactly. Just use cosine and sine for that. We have that angle. So cosine of 45 degrees, sine of 45 degrees, it's 0 and z. So we just have 0.7071, 0.7071, 0. And so then the angular velocity is just equal to, we're given that the angular speed is 10 radians per second. So it's just that speed times the direction. So 10 times 0.7071, 0.7071, 0. And so you get 7.071, 7.071, 0. And that's the angular velocity in radians per second. And what's the angular acceleration? 0, yep. And so now we can say the velocity of p observed is just equal to omega cross r. What's the r vector? So the r vector goes from the center of the circular motion to the point you care about. So here's p. Here's our r vector. Right. So r is equal to 0.6, and then you have to find this angle, and it's, I guess that's cosine of negative 45, sine of negative 45, 0. Can someone multiply that out? You can just multiply one of these. Okay, so 0.42426. This one's negative. And so the velocity of P observed is 7.071, 7.0710, crossed with 0.42426, 0.424260, and you get 0, 0, negative 6. And then for the acceleration observed, what delicious summery fruit are we going to use? Yeah. Okay, so we're going to use watermelon equation. This one goes away. There's no angular acceleration, so we just have 7.071, 7.0710, cross quantity 7.071, 7.0710, crossed with the r vector, 0.42426. I dropped off a negative here, but I think my answer is right because I just read that answer off my... So this is negative 0.42426, and I think you get negative 42.43, positive 42.430. That's a centripetal acceleration. In this case, since there's no angular acceleration, so all that's left is that centripetal acceleration. So you know it has to point from P towards the center. Okay, so now we have everything finally that we need to plug back into the big equation for the acceleration of P. That's equal to the acceleration of P observed plus capital Omega dot cross P plus 2 times capital Omega cross the velocity of P observed plus capital Omega cross quantity Omega cross P. So we have negative 42.43, positive 42.43, plus this one goes away because we don't have any capital Omega dot. Then we have 2 times Omega was 0, negative 5, 0, crossed with our observed velocity vector, which is 0, 0, negative 6, plus capital Omega cross quantity capital Omega cross the position vector, 1.131.2830. And we come up with 6. I don't have it.
Negative 10.7100.
Ooh. Imagine the odds. I guess 1 in 100. Okay. And then what else?
0, 0.
Oh, those are the components. Okay. Huh. Weird. Anybody else confirm that? Let's just hope that's right then. Anybody have any questions about that one? All right, let's do that one again now, but with a new coordinate system. Again! Do you like doing these? The world is totally split. The world, not the world. The world is mostly split into people who don't want to do this in the first place in any way. But the engineering world is split very clearly into people who really like looking at the same problem over and over again multiple ways, and people who just despise it and want to move on to the next thing. So you can think to yourself about which one you are and learn something about yourself today. As you can tell, I really like how else could we do this? Do the answers match? You know, I like that. I feel like that helps me understand this method better.
Does it also depends if it's Monday or Friday?
Yeah, probably a little. Yeah.
And if it's morning or evening?
Yeah, you're right. That kind of stuff, I'm sure, does affect it.
You could teach like a philosophy for math.
Yeah. Philosophy for engineers. Philosophy for scientists and engineers. Okay, so we got the same thing happening. We still have this rotating at 5 radians per second. We still have this one rotating at 10 radians per second. And all the lengths are still the same. But where are we going to put the coordinate system this time? Yeah, exactly. So we'll put it fixed at the center of the disk. And if we do this and get the same answers as the first one, and you go back and look at all the changes and all these many different vectors that go into these calculations, therein lies the secret. The secrets. Do you understand? Okay. All right, so
Philosophy, huh?
it's not really philosophy, but okay. So the first thing we need to figure out is, so we're going to use, and this is P again. We're trying to find. We're trying to find the acceleration of P. So we're going to use this formula. Well, okay. Before that, are the axes rotating? Yes, obviously. Now we have a different answer for this one, though. Is the origin accelerating? Yes. because it's moving around in a circular path like that. Okay, so the origin of the coordinate system is in circular motion around that orange axis. Okay, so we're going to have to use relative motion. So the acceleration of p relative to the ground, that's what we want, is equal to the acceleration of p relative to the origin plus the acceleration of the origin relative to the ground. This is a circular motion about that orange axis. And then the acceleration of p relative to the origin, we have to use this approach. It's equal to the acceleration of p observed plus capital omega dot crossed with p plus 2 times capital omega crossed with the velocity of p observed plus capital omega cross quantity capital omega cross p. All right, well, let's start out by calculating the acceleration of the origin relative to the ground. So how are we going to calculate that? Yes, yes. And mathematically, the way we're going to do it is the watermelon equation. I think, like intuitively, you're saying, yeah, it's a centripetal acceleration. You could just figure it out that way. But that's thinking, and when you think, you run into trouble. Okay? If I can convey anything to you in this semester, it's that. So instead of thinking, we're going to apply the watermelon equation because this is a circular motion, and we're trying to calculate an acceleration of a point moving in circular motion. So alpha cross r plus omega cross r. What's alpha? Yep. What's omega? Yep, right, exactly. And what's R? Well, actually, how long is that? Yeah. Oh, yeah. You're right. So all we need is the distance from this orange axis to where the origin is, and so that is, well, if you make this triangle, this is 45 degrees. That's 45 degrees. The hypotenuse is 1. And so R is just equal to positive 0.7071. That was the x-axis, right? And then 0, 0.
Is it wrong to include the y component for simplicity since it doesn't lead us to trouble?
So I guess, yes, if you could include that r vector could, if it's circular motion, so if it's spherical motion, there's a point. And it needs to be the vector from the point, from the center of the spherical motion, which is a single point, to the point that you're looking at. So you don't have any wiggle room. With circular motion, you're right that it's actually motion around an axis. And you could make your r vector go from anywhere on that axis. But I would do it, I would just choose the center of that circle and do it as that point so that you can treat it exactly the same as spherical motion. But yeah, you'll get the same answer. Okay, so the acceleration of the origin relative to the ground is equal to 0, 0, 0, well, plus 0, negative 5, 0, crossed with the quantity 0, negative 5, 0, crossed with r, 0.7071, 0, 0. And what do you get for that? In the negative x direction? 6775. Oh, really? Anyone else? Now we need someone else to do it. Okay. Sorry, Ken. Okay, so we're done with this, and we'll set it aside. So we're done with the relative motion part. Now we need to calculate the acceleration of p relative to the origin. So we're using this for the origin accel. So now we're going to deal with the rotating axes. We know that the acceleration of p relative to the origin is equal to the acceleration of p observed plus capital omega dot crossed with p plus 2 times capital omega crossed with the velocity of p observed plus capital omega cross capital omega cross p. And we just need to come up with all these vectors. So we're going to start with the easy ones, and then we'll go into the longer process of calculating the observed acceleration and observed velocity. Okay, so take a couple minutes and calculate those three things. Figure out what those three things are: the capital omega dot, and the position vector. Exactly the same as it was with the origin in the old location, because in both cases the axes are rotating the same as that rotating arm. The position vector is different this time. So omega is equal to 0, negative 5, 0. Omega dot is 0, 0, 0. And the position vector now just goes from the center of the disk to here. So that's 0.6 times 0.7071, negative 0.7071. And so that's, we had that earlier. That's this 0.42426. So 0.4243, I'll call it negative 0.42430. Any questions about those? All right, so now we need to calculate the velocity of P that's observed in the coordinate system and the acceleration of P that's observed in the coordinate system. So take a couple minutes and calculate those. Okay, so the observed velocity of P is going to be the angular velocity, lowercase omega, crossed with r. The acceleration of P observed is from the watermelon equation. So we need to figure out what omega and r and alpha are. Alpha is the easy one. What's that equal to? 0. What's omega equal to? That's right. So, and it's just the same as it was before. So the direction is at 45 degrees between the x and y axes. The magnitude is 10. So that's 10 times 0.7071, 0.7071, 0. So that's 7.071, 7.0710. And the r vector is the same as it was before, because the r vector always just goes from the center of the circular motion to the point that you care about. So that's the same as our position vector is this time. 0.4243, negative 0.4243, 0. And so now we can plug these in here. So for the observed velocity, we get 7.071, 7.071, 0, crossed with 0.4243, negative 0.4243, 0. What do you get for that?
Shouldn't that be the y component of that 7.07? Shouldn't that be negative?
No, because the axis of, so that's the axis of rotation. So it's according to the right-hand rule, so yeah, it's pointing straight up that way. Anybody have an answer for 0, 0, negative 6? And then anyone have an answer for this? So this goes away, and this is probably just the same as it was in the last one. Okay, so what do you get for this? What did we have before?
Before the negative 42.430, 42.430.
Okay. Okay. Well, so now it's just plugging that stuff into the into this equation. The acceleration of p. Let's finish next time, because then we have to combine it with the relative motion equation too, and I don't want to rush through all that.